Welcome to the second video in our study of thermodynamics. In the first video, which is linked in the description below, we saw that thermodynamics literally means the study of heat and work. That study is performed on systems which are well defined, and the direction of whether heat is gained or lost or work is done or added is indicated by the sign. Furthermore, that work or that heat could only be transferred by a perfect gas performing a process that is done reversibly. In this video, we're going to add a little bit of historical perspective on why these limitations were added, what the very definitions are that use heat and work, and what reversibility actually entails. Start off by studying heat. Mankind had been familiar with heat literally from the beginning. It cooked his meals, and he knew fire was hot. It did not take much longer for him to realize several other things, properties of heat. First of all, heat is proportional to temperature. If I have a very small flame, the temperature will rise quite slowly. If I add more heat with a larger flame, the heat rises quickly. Secondly, heat transfer depended upon what you are actually applying the heat to. For example, an aluminum cooking surface will transfer heat quite effectively, and the temperature will rise very quickly. However, a granite countertop insulates, so the same amount of heat will only produce a slow rise in temperature. That property of the material, whether it conducts heat well or not, is called the specific heat, and it is given in joules per gram degree Celsius. Quite often, even though units are annoying to remember, they do tell you the story. Exactly defined, the specific heat of any given substance is the amount of heat, given in joules, required to raise 1 gram of that substance by 1 degree Celsius. The third thing which was quickly noticed about heat was that how long it took to cook something depended on how big it was. It takes a lot longer to cook a turkey for Thanksgiving than it does a chicken. This dependency on mass is shown with a simple pot of water. If I have a small pot with a little bit of water, it will heat up rather quickly. However, a larger pot, still filled with water, given the same amount of heat, the temperature will rise quite slowly. Quite well understood by our ancestors for a very, very long time. They realized that the amount of heat generated was proportional to how hot something got, the rise in temperature. Also, some things heated up easier than others. That's a property of the material now called specific heat, lowercase c, where once again you see that units can be annoying, but they also tell the tale. Specifically, the specific heat is defined, as per the units, as the amount of heat, in joules, required to raise 1 gram of a substance by 1 degree C. Additionally, the amount of time it took to heat something up depended upon the mass. Large dinners took longer to cook than small ones did. So you wound up with a relationship from general chemistry, where the heat flow was equal to the mass times the specific heat of the material times the change in temperature. This definition, however, is not quite satisfactory for thermodynamics. Specific heat is again an intrinsic property of the material, but that is independent of the mass. Thermodynamics, on the other hand, deals with a system as the whole. Going back to the example of the pots of water, even though one pot was smaller, one was larger, one had less water, one had more water, both of them are complete systems. Therefore, thermodynamically, heat flow is expressed as dq is equal to capital C, which is the heat capacity of the entire system, times the change in temperature. This is applied to a perfect gas, which follows PV equals nRT. Within the gas law, for now, we will just safely ignore N, the number of moles of the gas, because that is simply a scalar. Twice as many moles would require twice as much heat. T is actually in the equation. The temperature is proportional to the amount of heat that is flowing. That leaves two independent variables, volume and pressure. For a perfect gas, these affect the heat capacity. If the volume is kept constant, you get what is known as C subscript V, the heat capacity at a constant volume, which has a value of 3/2 times the gas constant R for a monatomic gas, or 5/2 R for a diatomic perfect gas. If pressure is held constant, you get a heat capacity at a constant pressure, where C sub P is equal to 5/2 R for a monatomic gas, 7/2 R for a diatomic gas. And through the gas law, you'll notice that these two are actually related to each other. At all times, either for an ideal gas or a real gas, the difference between the heat capacity at a constant pressure and at constant volume is simply R, 8.314 joules per mole degree Kelvin. And this is derived because R is the potential energy of 1 mole of freely moving particles, the definition of a perfect gas. So if I have a monatomic gas at a constant volume, it has 3 degrees of freedom. It can move in the X, Y, and Z directions. So therefore, CV for a monatomic gas is 3/2 R. At a constant pressure, that gas can also increase volume or increase temperature. So that's additional 2 degrees of freedom. So you get 5/2 R. The heat capacity is defined with 1/2 R, 1/2 the gas constant, for each degree of freedom. So heat flow was quite well understood for a very long time. Similarly, so was work. Work. Force applied to a distance. What goes up must come down. Even your dog knows that energy goes from high to low, and it will follow the path of the ball. However, dynamically, the definition of work has historical context, which winds up being very important to understanding thermodynamics as a whole. Although people knew about fire and work for literally hundreds of thousands of years, thermodynamics was not studied as a discipline until the late 1700s to the early 1800s, the late 17th, 18th to the early 19th centuries. There was a good reason for that, and it goes to the historical context. That period of time was a period of revolutions. In 1776, in North America, a bunch of people decided that they didn't want to pay their taxes to a king on the other side of the ocean, so they went and founded their own country. That gave other people bright ideas. In 1789, a bunch of people in France decided that they didn't want to pay their taxes to a king who actually lived in France, so you had the French Revolution. At the same time, another revolution was going on that had long-lasting impacts across the world. In 1769, the Industrial Revolution started. This started when James Watt was able to perfect the first steam engine. This event was the spur that led people to start studying thermodynamics as a science. For starters, what a steam engine does is it takes heat for the purpose of producing steam, and that steam then moves a piston which produces work. That work was used to run factories and railroads and ships and essentially change industry by running everything with steam. However, there was a minor problem. These early steam engines had a terrible capacity to explode unexpectedly, which is why people started studying thermodynamics, because it would be much more economical to make ships that didn't explode as opposed to ones that did. That led to the thermodynamics of what work is. Work, thermodynamically, is the result of an expanding perfect gas moving a frictionless cylinder against a constant pressure. So mathematically speaking, dW is equal to minus the external pressure times the change in volume, where the negative sign is in there because, once again, sign is given in direction. By expanding, by performing work, the gas is losing the ability to perform further work in the future, so dW is negative. So, dynamics is the study of heat and work. We have heat as some specific heat times the change in temperature. We have work as minus an external pressure times the change in volume. Then there's the small fact that all of these things have to be done reversibly in order to get an answer. Reversibility, once again, is a process performed in an infinite number of infinitesimally small equilibrium steps. At first, this would seem to be impossible because it would take forever, and it actually would take forever. But why it is important for thermodynamics can be explained rather simply with another everyday item. Everybody has probably been faced with the prospect of having to open up a bottle of soda, where the inside of the bottle is at some high pressure because maybe you dropped it, and the outside of the bottle is at a lower pressure, just the atmospheric pressure. You also know the worst way to open this bottle is simply in one step, to pop the top. If you pop the top, two things happen. First of all, you hear a hiss. That is the gas pressure equilibrating with the outside. After the gas leaves the bottle, the volume then expands. You look at the definition of work as P delta V. The work done by the gas in this process is minus P2V2 minus P1V1, or very simply, the area under the curve shown. If you are faced with a bottle that might explode, most people know that instead of just opening it and make a mess in one fell swoop, the best way to do it is to use several steps. Open the bottle, close it, open it, and close it. So what happens if instead of opening it once, we open and close it 3 times? Each step, a little gas escapes, the volume increases slightly, and now, instead of that gas performing work in 1 step, it performed it in 3 steps, where the total work is the work done by opening the bottle once, plus the second time, plus the third time. If I really want to be careful, I'll open and close the bottle 5 times to minimize the mess. Once again, each one of these steps is producing an independent amount of work. So the total work is going to be the first plus the second plus the third and fourth and fifth times you open the bottle. What you will notice is that work is always the area under the curve. And just looking at these pictures, doing more steps produces more work. The area under the curve for opening the bottle 5 times is greater than the area under the curve for opening it 3 times, is much greater than the area under the curve than just letting the gas escape in one step. If I theoretically had a reversible process and opened that bottle an infinite number of times and closed it infinitely quickly, I would have an infinite number of very, very tiny steps. So the total work I would do would be adding up all of those little infinite steps. Math comes into this because the definition of an infinite sum is an integral. So we now have the very, very first definition of a thermodynamic property. Reversible work is defined as the integral of minus p dv. And the meaning of reversibility also becomes important. Why is reversibility so important? The definition of an integral is that it provides the maximum area under a curve. Therefore, a reversible process is going to produce the maximum amount of heat or work possible for that process. And at this point, it just becomes sort of simplistic. That's the only outcome a person can know. If you're taking a test, before you take the test, you know that the most you can get on the test is 100, but you don't actually know what you're going to get. So the theory behind thermodynamics depends on reversibility because the best outcome is the maximum outcome and is also the only predictable outcome. In our next video, we will look into how a knowledge of how reversible processes work and a definition now of what work and heat are lead to other thermodynamic principles. The next video is also linked in the description below.